Now let's consider another situation. Here we have an exponential forcing function. So notice that we have an exponentially decaying external force on the system. That is, the initial force from the spring mass system is large, but then quickly dissipates. We should observe that the spring mass system has some intense initial behavior, but that it then quickly returns to its normal behavior. So let's think about the size of this. So this has to be in newtons, which is equal to kilograms multiplied by meters per second squared. So you can kind of think about it as a similar to the force that we had up top, except this force is going to change over time. And if we look at the force, the F sub force, which is this function here, it's going to start off at time 0 at a force of 20 newtons. But as t passes, so let's just say after 1 second, this will be approximately 7 or 8 units. So this thing will really rapidly drop, and as t becomes infinitely large, this force really goes away. That's going to happen pretty quickly, because by the time you raise this to the second or third power, this force is now down here at 1 newton. So it'll have some initial intense behavior. Eventually, once that force loses its momentum, then we're just going to be focusing on the spring mass system. Now here's the thing, this force could be intense enough to where, because this thing is damped, it will just damp a lot faster than it would if we didn't have that forcing function. Okay, now we already know y sub h, so we're not going to derive that again, because y sub h is just going to be the solution to the homogeneous equation y double prime plus 3y prime plus 2y equals 0, and we solve for that up above. The only difference between these two equations is the non-homogeneous forcing function. So this is still going to be k1 e to the negative t plus k2 e to the negative 2t. All we have to focus on now is just the non-homogeneous component. So the non-homogeneous component is going to be now postulating a guess for y double prime plus 3y prime plus 2y equals 20 e to the negative t. Now the only way for these three functions that are just derivatives of this original to add up to an exponential is for the original function to be exponential. So my guess is going to be y equals something, I don't know what, but something e to the negative t. That coefficient is undetermined. I'm going to determine it. So let's take its derivative, which will be negative c e to the negative t. And let's take its second derivative. I'm going to make a quick change to this function for a reason that I won't go into here. I'm going to make this e to the negative 0.5t. So that won't affect anything that we've done already. We'll have a little bit of a problem if we leave it as negative 1t, but let's make it e to the negative 0.5t. So that means our guesses here are just going to have, well, I guess that will change. This will be negative 0.5t, and this will be negative 0.5 c e to the negative 0.5t. And the second derivative will be positive 0.25 c e to the negative 0.5t. And so what would have happened is if I left it as negative t, these three would have added up to 0, and so we would have had to update our guess. And I don't want to get into that right now because it's just a detail that is better left for another time. So now we plug these guys in. So we have y double prime plus 3y prime. So that's going to be 3 times negative 0.5 is going to be negative 1.5 c e to the negative 0.5t. Plus 2 times 0.25 will give me plus 0.5 c e to the negative 0.5t equals 20 e to the negative 0.5t. Now again, you could see this as factoring out a e to the negative 0.5t. What I see here is that plus that have to equal 20 e to the negative 0.5t. So, I'm sorry, just have to equal 20. So this coefficient plus this coefficient plus this coefficient has to equal this coefficient. So 0.25 c minus 1.5 c plus 0.5 c has to equal 20. And again, if you factor that in e to the negative 0.5t, then you'd see that the coefficient of the sum of these will just be this expression down here. If I add these together, this will give me negative 0.75c has to equal 20. And double check my work there. I think that seems right. So c is going to equal 20 divided by negative 0.75, which comes out to about negative 26.7. Negative 26.7. Not exactly, but close enough for our purposes here. So that means we've just found that y sub p has to be, with its now determined undetermined coefficient, negative 26.7 e to the negative 0.5 t. So we're going to add these two guys together to get the general solution. General solution is going to be k1 e to the negative t plus k2 e to the negative 2t minus 26.7 e to the negative 0.5 t. So as t approaches infinity, regardless of what these coefficients are, all three of these terms are going to go to 0. You raise something to a negative power that's large enough, it will go to 0. So to find our initial condition, we need the velocity function, which is negative k1 e to the negative t minus 2k2 e to the negative 2t, and negative 0.5 times negative 26.7 comes out to about 13.35. So plus 13.4 e to the negative 0.5 t. So now I substituted my initial conditions, and so the same initial conditions as the last problem, just so that we can compare these and see how they behave differently. So this one's going to get 0, initial position, equals k1 plus k2 minus 26.7. So t is 0. And then initial velocity is negative 1 equals negative k1 minus 2k2. But now, when that's 0, we'll have plus 13.4. So going to Wolfram alpha, and we get k1 equals 39, k2 equals negative 12.3. So our final solution is going to be y equals 39 e to the negative t plus, or I should say minus, 12.3 e to the negative 2t minus 26.7 e to the negative 0.5t. So we're now ready to graph this. Again, we can see that as t approaches infinity, these three terms will all go to 0. And here's what we get. So we do see that there's that initial condition that the spring mass system does successfully stretch, or rather compress, and then returns back to rest. Now that's as opposed to not having that term in there. Again, wrong initial condition, but this thing rapidly returns to rest. But with that term, we get a little bit of an oscillation before returning to rest. In fact, we can see that it still does its thing, it still goes to rest, but because of that forcing function being applied, we do get a little bit of a hiccup here. So if we wanted to model this, we could call this f of x over here. And just to see what that spring mass system would do, let's plot the point 0, comma f of t. And now we'll say t equals 0 and set our slider for time from 0 to about, we'll say, 15 seconds. All right, so I'm going to zoom this in a little bit here. We'll go from time 0 to about time, we said we wanted to go about 15, so there we go. So there's that initial movement. Watch this little dot here as we press play. Slow this down a bit, make it move forward just once. So there we go. Not super exciting, but if you're designing a suspension system, maybe that is very exciting. Great, so there we have our final solution. And let's take a look at one more situation. So I hope these have been kind of intuitive situations to give us a little bit of a sense of what's going on. Here, the reason I think that we were able to get that oscillation, that initial that initial desire for that mass to move into a compression state. Here it was blocked off because the mass was heavy and it was constant. So notice that our force here was 98 newtons, a constant 98 newtons. But our force down here, 20 e to the negative 0.5 t, that initial force is only 20 newtons, and it quickly dies off. So I think that even though there is something that is sitting on top of that mass, if you will, another mass on top of the mass, it sort of starts to diminish. Maybe it starts to evaporate slowly. But just to give you a little bit of a visual, I'm saying that.